Have you ever looked up at the night sky and wondered where stars come from? These twinkling points of light, scattered across the vast expanse of the cosmos, are not eternal. They have a beginning, a middle, and an end. Their stories are tales of immense energy, unimaginable gravity, and the ceaseless dance of matter and energy. Our journey begins with nebulae, vast clouds of gas and dust that drift through space. These nebulae, often called star nurseries, are the birthplaces of stars. Imagine a cosmic cloud, a swirling mass of hydrogen, helium, and traces of other elements. This cloud, shaped by gravity, begins to collapse in on itself. As it collapses, it spins faster and faster like a figure skater pulling their arms in during a spin. This spinning motion flattens the cloud into a disc-like structure. At the center of this swirling disc, gravity pulls more and more material inward. The temperature and pressure at the center increase dramatically as the gas compresses. Eventually, the core of the collapsing cloud reaches a critical temperature, millions of degrees Celsius, hot enough to ignite nuclear fusion. Hydrogen atoms fuse to form helium, releasing an incredible amount of energy in the process. This burst of energy prevents further collapse and marks the birth of a star. The newly formed star, called a protostar, is still surrounded by a disk of gas and dust. This disk, known as a protoplanetary disk, may eventually give rise to planets, moons, and other celestial objects. Think of our solar system, born from a similar disk billions of years ago. Our Sun, once a fledgling protostar, ignited and bathed its surroundings in light and heat. The protostar continues to gather material from its surroundings, growing in mass and luminosity. As it gains mass, its gravitational pull increases, attracting even more gas and dust from the surrounding nebula. This process can continue for millions of years, shaping the protostar and influencing its eventual fate. The life cycle of a star is a delicate balance between gravity, which seeks to compress the star, and the outward pressure generated by nuclear fusion in the core. This balance, known as hydrostatic equilibrium, determines the star's size, temperature, and brightness. This equilibrium, however, is not permanent. Once a star achieves a stable state of nuclear fusion, it enters what is known as the main sequence. This is the longest stage in a star's life, and it's where our own sun spends its days. During this phase, stars fuse hydrogen into helium in their cores, releasing a steady stream of energy in the form of light and heat. The color and brightness of a main sequence star depend on its mass. Massive stars, many times larger than our sun, burn through their fuel much faster than their smaller counterparts. These stellar giants shine brightly, but live relatively short lives. Smaller stars, on the other hand, sip their fuel slowly, extending their lifespans for billions of years. Our Sun, a yellow dwarf star, is about halfway through its main sequence lifespan. As a star exhausts the hydrogen in its core, it begins to evolve off the main sequence. The core contracts and heats up, while the outer layers expand and cool, transforming the star into a red giant or supergiant. Red giants are colossal stars with cooler surface temperatures, giving them their characteristic reddish hue. Section 4. Stellar fireworks, supernovas, neutron stars, and black holes. The fate of a star after its red giant phase depends on its mass. Smaller stars, like our Sun, will eventually shed their outer layers, forming planetary nebulae. The remaining core, a dense, hot object called a white dwarf, will slowly cool over billions of years. Massive stars, however, are destined for a more dramatic end. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses rapidly, triggering a catastrophic explosion known as a supernova. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. The remnants of a supernova explosion can take many forms. The core may collapse into a neutron star, an incredibly dense object composed primarily of neutrons. Neutron stars are so dense that a teaspoonful of their material would weigh billions of tons on Earth. If the core is massive enough, it may collapse further, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Section 5. Our place in the cosmos. The enduring fascination with stars. Stars have captivated humanity for millennia. They have guided our ancestors across vast oceans, inspired countless myths and legends, and continue to fuel our curiosity about the universe we inhabit. From the ancient astronomers who charted the constellations to modern astrophysicists who study the intricate processes within stars, we have always sought to understand these celestial objects. Stars are not merely distant points of light, they are the building blocks of galaxies, the crucibles where heavy elements are forged, and the engines that drive the evolution of the cosmos. Their birth, life, and death are intimately connected to our own existence. The elements that make up our bodies, the air we breathe, and the earth beneath our feet were all once part of a star. As we continue to explore the universe, unraveling the mysteries of stars, we gain a deeper appreciation for the interconnectedness of all things. The study of stars allows us to trace our cosmic lineage, to understand the processes that govern the universe, and to marvel at the sheer beauty and wonder of the cosmos.